welcome back. Our chapter 4 is going to cover uniform circular motion and gravitation. Today's video will cover uniform circular motion. The definition for that is the movement of an object at a constant speed around a circle with a fixed radius. We're going to apply Newton's first two laws to objects that are moving in a circle instead of a straight line. So the first law, for an object moving in a circle at a constant speed, but remember the velocity is varying, okay, it must be experiencing a force. The speed can be constant because that's a magnitude, but the velocity will be changing because the direction is constantly changing as you move around a circle. So if an object is moving at a circle at a constant speed, it has to be experiencing a force, otherwise it would travel in a straight line. So if you consider a circle, you can go ahead and label the radius on your copy. The velocity would be in a direction that we call tangent to the path. And you can also note that it kind of makes a right angle with the radius. You want to think of the direction of the velocity as if I were to move something and say swing it in a circle and I let go, the way that it would travel in that straight line, once I were to let go of my object, it would travel off in that direction tangent to the circular path. So I mentioned this on the previous slide, but just to remember the difference between scalar and vector quantities, scalar quantities can only change in magnitude, but vector quantities can change in magnitude, direction, or both. So in this case, since we're interested in the velocity of our object moving around in a circle, this is a vector quantity, and it's only changing in direction only because we are moving at a constant speed. And in circular motion, the direction of the velocity is always tangent to the path. And remember, you can think of that as a right angle to drawing the radius of your circular path. Some characteristics we're going to discuss about an object moving in uniform circular motion will be period, frequency, and speed. So we'll do some definitions and equations. The period is the time needed to complete one full rotation or revolution. It's represented by the variable capital T, and it's going to be measured in seconds. So we'll write our units as an S for the seconds. The next thing is called frequency, and this would be something that's probably new to you. The frequency is the number of rotations or revolutions per unit time. You can think of it as the opposite of the period. Instead of saying the time measured for one rotation, it would be the number of rotations in a particular amount of time. And that time we're interested in is still going to be the seconds. The frequency is measured or represented by the variable lowercase f, and it's measured in what we call hertz, which would be Hz for the abbreviation. And just as a side note, since we're interested in the number of something per unit time, I could look at my hertz and write them as the number of something. So I would just put a 1 as a placeholder in the units per second. So a hertz would be the same thing as an inverse second, or in your math classes, you may have seen seconds to the -1 as a way to write the inverse. But typically, you'll see hertz as the units. The period and the frequency are inversely related to each other. That means as one quantity increases, the other one will decrease. They're going to behave as opposites. And our equations can be written as follows. If we're solving for the period, we would simply write 1 divided by the frequency. Or if we're solving for the frequency, we would write that as 1 divided by the period. They are going to be inverses of each other. In previous chapters, we've talked about speed. However, that was in a straight line. Now, when we look at the speed of something moving in a circle, that object is traveling a distance around the perimeter of the circle. So for example, if a car had a constant speed of 7 meters per second, that means that it would travel 7 meters along the perimeter in each second of time. So we're going to come up with an equation to write the speed for an object moving in circular motion. Since the distance covered for an object moving around the circle once around the perimeter is called the circumference. Hopefully you remember that you find circumference by doing 2 pi over r. Typically when we had looked at the speed previously, we simply said distance over time. But for a circle specifically, the speed would be 2 pi r, And then our time would be the period. So distance for an object moving in a circle is the circumference, and then the time once around a circle would be the period. The units are still going to be meters per second, just like in previous chapters. So let's do an example problem. We have a car traveling at 125 revolutions per minute. Whenever you see per and then any amount of time, that's going to refer to a frequency. So we'll go ahead and label that. Notice that for the units, I did a 1 as a placeholder for revolutions because that's just a number, and then per minute on the bottom. And we have a track with a radius of 30 meters. And we are asked to find the period and the speed. So remember that period is going to be measured in seconds, so we are going to need to make that conversion, but let's go ahead and set up the problem. So my equation is the period is 1 divided by the frequency, and I plug those numbers in. And this gives me a period of 0.008, and when I divide 1 over minutes, that turns my units into minutes. So now we need to convert that to seconds. There are 60 seconds in a minute, and I'm going to be multiplying so that my minutes cancel out. And this gives me a final answer of a period of 0.48 seconds. Next, we want to find the speed. And if you remember our equation, since we're moving around in a circle, the distance traveled would be equal to the circumference of the circle, and then the time that we divide by is going to be the period that we already found. So let's plug in our numbers. And when we plug everything in, if you followed along, you should get a value for the speed of approximately 393. Our radius was already in meters, and remember we converted the period to seconds, so we do get units of meters per second, which is accurate for speed. Next, we're going to look at the ideas of acceleration and force, but for objects moving in a circle. So we call this the centripetal acceleration, and whenever you see the word centripetal, I want you to think about the object moving around in a circular pattern. The formula for this is going to be the acceleration, and we put a little subscript of a c for centripetal. It's going to be the speed squared divided by the radius. The units are still going to be meters per second squared, just like you're used to seeing for objects that move in a straight line. So the units don't change. The direction for the centripetal acceleration is toward the center of the circle, and this means that it will end up being perpendicular to the velocity. Next, we're going to look at centripetal force, and we do still apply Newton's laws because remember, the object must be experiencing a force in order to travel in that circular motion, otherwise it would have gone in a straight line. So we do know that there is going to be an acceleration. So what we're doing is starting with Newton's second law, which is F equals ma. We do only have one force at this time, so our net force is going to be the actual centripetal force. So we're going to put a subscript of a c to indicate that it's centripetal. And remember, when you see that word, it simply refers to an object moving in a circle. And we're going to be multiplying by the mass times the centripetal acceleration. So now we're dealing with both of those things, the force and the acceleration, referring to an object moving in a circle. I'm going to make a quick substitution over here. We're going to substitute in the formula for centripetal acceleration, and that's going to give me mass from here times, and then instead of acceleration, I'm going to write v squared over r. And then once we put all of that together, that gives us a final formula of the centripetal force is equal to the mass times the speed squared or velocity squared divided by the radius of your circle. And just like all of our forces in the previous unit, this one will still be measured in newtons. And also, from the dynamics chapter, we noticed that the force was directly proportional with the acceleration. They were in the same direction, and the same is going to hold true for objects moving around in a circle. So just like the acceleration was directed toward the center of the circle, the force is directed toward the center of the circle as well. Now I know this might be a little bit difficult to visualize, so we are going to have some demonstrations in the classroom. So I want you to remind me when you get to class to ask to see the demonstrations. And they are some of my favorite ones. Some of you might end up making a mess, but that's okay because we're going to have fun when we go over those. For our example problem, I'm going to get you set up and identify all of the variables, and then I would like you to try the example on your own and then come back, pause the video, try it out, and then come back and see if you were correct. So we've got a mass of 1,200 kilograms, a radius of 30 meters, and a velocity of 8 meters per second. Notice that I did not include any sort of direction in front of my velocity because it is constantly changing direction since you're moving around a circle. And then mathematically, we're only interested in the magnitude, which means just the number. So even though it says velocity, when we write that down, we are going to use the magnitude, which would be the speed when we plug into our formula. So previously, you should have the formula for centripetal acceleration. We're going to take the speed squared, or the velocity squared, and divide it by the radius. So pause the video and try that out. So I hope you were able to get an answer of 2.1 meters per second squared. If you did not, take a moment and pause the video and write down all the steps that I showed you. Next, we need to find the centripetal force. From your notes, you should see that centripetal force is mass times the velocity squared over the radius. So go ahead and pause the video, plug your numbers in, and come back and check your answer and see how you did. You should have gotten an answer of approximately 2,560 newtons. I did go ahead and show you the derivation of the units on how the kilograms, the meters per second getting squared and dividing by the meters turns into a newton. However, as long as you remember to put newtons as part of your answer, I'm going to be happy and you will get full credit. Our last section is to determine the difference between centripetal and centrifugal. These are two words that people sometimes use interchangeably, but they are in fact different. Centripetal is an actual physical force directed toward the center of the circle. That's the thing that keeps the object moving in a circle and prevents it from traveling in a straight line. Centrifugal, on the other hand, is a fictitious, non-existent force. It's more of a feeling. And I don't know if you've ever been in a vehicle and it makes a really sharp turn and you kind of feel like you're thrown toward the outside of the door, maybe the outside of the car. But that feeling you get of being thrown outward away from the center is what we call centrifugal. However, this is merely the object's inertia being directed in a straight line. So if you think about you're trying to go forward and then all of a sudden the car you're in makes a sudden turn, your body's inertia is still trying to move in that forward direction that you originally had in a straight line, but the car is moving and turning, so you're actually hitting that outside of the car. So you feel like you're being thrown outward, but you're actually just simply trying to continue in that original straight line. On your test, I will ask you the difference between these two. Remember that centrifugal is fictitious. It's only a feeling, and the reason for it is because of your inertia. Centripetal, on the other hand, is an actual physical force that is directed toward the center of the circle. So in our car example, that would be the actual door of the car that holds you in and keeps you from flying outwards. So again, on your test, you'll need to know the difference between the two, which one is the real actual force and which one is merely a feeling, and then you'll need to know what causes that sensation of being thrown outward. And the answer for that is your inertia. So I hope I've summarized these notes pretty well. We are going to have some example problems to do in class. We have several demonstrations that are really fun. I'm looking forward to them. And then we're also going to have some online simulations so that you can kind of get some more practice with these equations today. Good luck, and I'll see you in class.